The surface looks still, almost empty. A film of meltwater slides over ancient rock. Sunlight fractures into cold shards and then disappears. In the thin space between liquid and ice, life presses itself into invisibility. Cells slow, chemistry hesitates, time stretches, and yet, something here refuses to vanish. It does not swim or hunt. It does not flee. It waits. Under pressures that would rupture tissues, under radiation that shreds DNA, under dehydration so complete that metabolism nearly stops. This organism endures without drama. It neither conquers nor adapts in ways we easily recognize. It simply persists, outlasting conditions that erase almost everything else. For centuries, it escaped notice not because it was rare, but because it was small enough to be ignored. Only when microscopes sharpened did its quiet defiance become visible. And with that visibility came unease, because its biology does not follow the rules we assume are universal. Today, we're diving into why nothing about tardigrades was normal, and why their existence forces biology to confront its own limits. Asterisk life usually announces itself through motion. It grows, feeds, reproduces, and competes. It responds quickly to heat, cold, hunger, and threat. For most animals, survival is a constant negotiation with the environment, an active process that collapses the moment conditions slip beyond. Tolerance tardigrades exist outside that pattern. They are found in places where biological activity should be brief or impossible. Mosses that dry completely between rains, liken exposed to freezing nights and scorching days. Sediments at the bottom of lakes that cycle between oxygen and anoxia, even the thin films of water that form temporarily on glaciers or rock faces. These are not stable habitats. They are biological trapdoors, environments that repeatedly cross the boundary between livable and lethal. Most animals avoid such places or survive only fleetingly within them. Tardigrades do neither. They remain. Extreme survival in most of biology is about tolerance within limits. Polar fish produce antifreeze proteins but still require liquid water. Desert mammals conserve moisture but cannot dry out entirely. Bacteria form spores, but spores are not animals. They are simplified survival states stripped of movement, digestion, and complexity. Tardigrades break this categorization. They are animals with organs, muscles, nervous systems, and reproductive structures. Yet, when the environment collapses, they do not flee or adapt behaviorally. Instead, their biology abandons its usual rules. When water disappears, metabolism slows not by degrees, but by orders of magnitude. Chemical reactions that define life nearly halt. Cells contract and reorganize. The animal curls inward, becoming something that is no longer actively alive in the conventional sense, but not dead either. This challenges one of biology's quiet assumptions, that life must always be doing something in laboratory conditions. Tardigrades survive temperatures near absolute zero and brief exposure to extreme heat. They endure radiation levels hundreds of times higher than what would kill a human. They persist in vacuums that strip unprotected tissues apart. None of this relies on repair after damage. The damage largely never happens. The environments that select for this ability are not constantly extreme. They are unpredictable. Dry for 1 week, flooded the next, frozen overnight, irradiated by sunlight the moment clouds part. Evolution in such settings does not reward speed or aggression. It rewards patience and reversibility. For tardigrades, survival is not about resisting extremes. It is about stepping outside of them. This is where their biology diverges most sharply from ours. Humans survive extremes by maintaining internal stability, body temperature, hydration, and oxygen levels. When those controls fail, death follows quickly. Tardigrades do the opposite. They surrender stability entirely, collapsing into a controlled shutdown that preserves structure without activity. In doing so, they blur definitions. Scientists rely on, if metabolism nearly stops, is the organism alive? If reproduction can resume after decades of suspension, was it ever truly gone? Extreme environments usually filter life down to its simplest forms. Tardigrades show that complexity does not always vanish under pressure. Sometimes it learns how to wait, and that waiting's reversible and biologically unprecedented, where the real story begins. Asterisk, asterisk. It does not harden into a shell or retreat into a protected chamber. There is no bunker, no external armor. The transformation happens internally, at a scale measured in molecules. The trigger is often dehydration. As water evaporates from its surroundings, a tardigrade begins to lose the very substance that makes chemistry possible. In most animals, this is catastrophic. Proteins collapse. Membranes rupture. DNA strands break as structures lose their shape. Death follows quickly, not because of one failure, but because everything fails at once. Tardigrades take a different path. As water leaves their cells, they actively reorganize what remains. The animal contracts into a compact form known as a ton. Legs withdraw. The body shortens. Inside, metabolism does not simply slow, it nearly disappears. Oxygen consumption drops to levels so lothothy approach the limits of measurement. Enzymatic reactions that define living cells pause, suspended in a state that is neither functioning nor broken. The key lies in how tardigrade cells handle absence. Most organisms rely on sugars like trehalose to protect cells during drying. Tardigrades, surprisingly, use very little of it. Instead, they produce unique proteins found nowhere else in the animal kingdom. These proteins do not act like enzymes or structural fibers. They act like EHOLDERS. As water vanishes, these proteins form a glass-like matrix inside the cell. This process, called vitrification, locks cellular components in place. Membranes cannot collapse because they are held in position. Proteins cannot misfold because their shapes are stabilized. DNA strands remain aligned, shielded from the physical stresses that normally tear them apart. It is not repairable. It is prevention. Radiation offers another test. High-energy particles slice through cells, snapping DNA like thread. In humans, this damage accumulates quickly and irreversibly. Tardigrades endured doses that should erase genetic information entirely. Part of the reason is physical shielding. Tightly packed DNA is harder to break. But there is also active protection. Specialized proteins bind directly to DNA, reducing the number of breaks radiation can cause in the first place. Even when damage does occur, the shutdown state buys time. With metabolism paused, harmful chemical reactions cannot cascade. Errors do not spread. When water returns and life resumes, repair mechanisms activate slowly and deliberately, correcting what little damage slipped through. Freezing presents yet another challenge. Ice crystals puncture cells from the inside. Tardigrades avoid this not by resisting ice, but by removing the water that would form it. With so little free water remaining, crystals cannot grow. The cold becomes irrelevant. What emerges is a radical biological strategy, survival through near-total inactivity, enabled by molecular foresight rather than resilience. This is not immortality. It is extreme conservatism at the cellular level, refusal to change when change would be fatal. The result is a body that can fall out of time, then re-enter it intact. And in doing so, tardigrades redefine what it means for an animal to be alive at all. Indestructibility in biology often comes with visibility. Thick shells, rapid regeneration, aggressive defenses, traits that dominate ecosystems and push competitors aside. Tardigrades possess none of these. They are small, slow, and largely invisible. Their strength does not translate into control. That contrast is not accidental. It is the product of evolutionary trade-offs that favor persistence over performance. Tardigrades reproduce modestly. Their life cycles are simple. Their population growth limited by the same environmental instability that shaped their survival strategies. Moss beds and lichens offer brief windows of activity, then collapse again into dormancy. There is little reward for speed or size when resources appear unpredictably and vanish without warning. In stable ecosystems, resilience alone is not enough. Faster animals claim food first. Larger ones displace competitors. Complex social systems amplify success. Tardigrades do none of this because their biology is optimized for a different battlefield, one defined by collapse rather than competition. Their near indestructibility carries costs. The proteins that stabilize cells during shutdown are energetically expensive to produce. Maintaining the genetic instructions for cryptobiosis requires space in a genome that could otherwise support growth, specialization, or sensory complexity. Every adaptation is an investment, and evolution does not fund redundancies lightly. As a result, tardigrades remain simple. Their nervous systems are functional but minimal. Their behaviors are limited. They do not hunt strategically or respond dynamically to threats. When conditions are good, they feed and reproduce quietly. When conditions fail, they withdraw entirely. This makes them poor competitors in environments that remain consistently favorable. They are easily outpaced by nematodes, rotifers, insects, and microbes that exploit stable resources more aggressively. Where others thrive continuously, tardigrades merely endure intermittently. Evolutionary success is often measured in abundance and dominance. By those metrics, tardigrades are marginal. But evolution does not operate on a single scoreboard. It rewards strategies that work across time, not just space. During droughts, freezes, radiation spikes, or chemical shocks, the ecological hierarchy collapses. Populations crash. Lineages vanish. In those moments, tardigrades do not rise, they remain. When the environment recovers, they resume life as if nothing happened, repopulating spaces emptied of competitors. This is no tan adaptation to one extreme. But to instability itself, their bodies are not built to win. They are built to wait out loss over evolutionary timescales. This strategy creates a paradox. Tardigrades change slowly. They do not need rapid innovation because their survival does not depend on fine-tuning to current conditions. This makes them conservative, but also resilient to extinction. They are not evolutionary. They are long-distance survivors in choosing persistence over dominance. Tardigrades reveal a quieter path through natural selection, one where success is measured not by how much life you take from the environment, but by how little you need to survive it. Asterisk, asterisk, on geological timescales, extinction is not an exception. It is the rule. Earth has erased most of the species that have ever lived. Asteroid impacts, volcanic winters, rapid climate shifts, oxygen collapses each reset the biological landscape, favoring traits that can endure sudden failure rather than gradual change. Dominance disappears quickly when the rules of survival rewrite themselves overnight. Tardigrades exist in the margins of these resets. Fossil evidence of tardigrades is scarce, not because they are new, but because their bodies are too small and soft to preserve isolate. Molecular data, however, places their lineage hundreds of millions of years deep older than many groups that once ruled the planet. They have persisted through multiple mass extinctions, not by resisting catastrophe, but by stepping outside its time frame. When ecosystems collapse, the problem is not death alone, it is continuity. Life depends on uninterrupted chemistry feeding, repairing, reproducing. Interrupt those processes for too long, and even surviving individuals become evolutionary dead ends. Tardigrades avoid this trap by pausing continuity itself. During global crises, water availability fluctuates wildly. Temperatures swing. Radiation levels spike as atmospheres thin or magnetic fields weaken. For most animals, these changes compound. For tardigrades, biology narrows to structure alone, carried forward intact while the environment reshapes itself. This has implications beyond their own survival. Ecologists studying resilience increasingly recognize that persistence does not always require adaptation to new conditions. Sometimes it requires insulation from conditions entirely. Tardigrades embody this principle at the smallest scale, surviving not because they fit future environments, but because they do not participate in them while they are hostile. That perspective reframes extinction. It suggests that vulnerability is less about sensitivity to specific extremes and more about dependence on continuous activity. Species that must constantly feed, regulate, and reproduce are exposed to interruption. Species that can stop safely are not. This insight has drawn careful attention from astrobiology and planetary science, not as speculation about life elsewhere, but as a framework for understanding where life could persist unnoticed. If life can survive long periods without metabolism, then habitable conditions need not be continuous. They only need to return occasionally on Earth. This may explain why tardigrades appear in places repeatedly stripped of life. Drying mosses, polar deserts, and alpine rocks, they are not pioneers. They are holdovers, bridging dead intervals until conditions improve. Their resilience does not make them immune to extinction. It makes extinction less urgent. Time becomes negotiable. In that negotiation lies their quiet power. While dominant species rise and fall with environmental stability, tardigrades remain threaded through deep time. Unchanged, not because evolution failed to shape them, but because it found little reason to. They survive not by mastering the planet, but by enduring its silences. Asterisk, asterisk, even after decades of study. Tardigrades resist closure. Their abilities are documented. They survive dehydration, radiation, freezing, and they resume life afterward. But the deeper question how long this can truly last remains unanswered. Experiments have revived tardigrades after years, even decades, in cryptobiosis. Beyond that, the data thins. At some point, molecular damage must accumulate. At some point, structure must fail. Where that boundary lies is still unknown. This uncertainty unsettles biology because it touches a line scientists rely on: the distinction between life and non-life. If an organism can suspend metabolism almost entirely for years at a time, yet retain the capacity to reproduce, is life defined by activity or by potential? Tardigrades force that question without offering a resolution. Their protective proteins are now studied intensely, but they have not been widely replicated in other animals. Why this strategy evolved so rarely remains a mystery. The environments that shaped tardigrades are not unique. Droughts, freezes, and radiation spikes occur everywhere. Yet complex animals rarely evolve the ability to stop safely. Something about this strategy is either exceptionally difficult to achieve or exceptionally costly to maintain. There are hints of hidden trade-off: subtle cellular damage that accumulates invisibly, reproductive costs after revival, limits to how often cryptobiosis can be entered without consequence. These costs are hard to measure because they unfold slowly, across lifespans that stretch discontinuously through time. Tardigrades may not be immortal. They may simply age differently, aging only when active, not when waiting. If so, then time itself becomes an environmental factor they partially escape. This reframes what resilience means: not toughness, not repair, but restraint. The ability to not react, not metabolize, not change, when change would be fatal. In a world increasingly defined by rapid environmental shifts, this biology feels unsettlingly relevant. Not because it offers solutions, but because it exposes limits in our understanding. We tend to imagine survival as action. Tardigrades suggest survival can also be refusal. They do not adapt faster. They do not evolve dramatically. They do not dominate. They persist, and in doing so, they remind us that life is not only about thriving under the right conditions, but about enduring the wrong ones, sometimes by stepping so close to the edge of non-existence that the edetric distinction itself begins to blur. Nothing about tardigrades is normal, and perhaps that is the point. Asterisk, asterisk. They do not conquer environments. They outlast them, while ecosystems rise, collapse, and reorganize. Tardigrades remain threaded through the gaps, silent during catastrophe, present after recovery. Their biology does not chase progress or complexity. It protects the option to continue. In their stillness lies a lesson biology has not finished interpreting: that survival is not always about strength, speed, or intelligence, but about knowing when to stop and how to begin again.